Okay, let's go ahead and start. I don't know if I'm not on y'all's guys' page. Let me go to the student view. Okay. So here's our homework assignments. This thing is bleeding off the edge a little bit. I don't know if I can fix that or not. But at any rate, there's our homework assignments. And that's still the same list as last week. I haven't added anything. Now, I slightly rearranged the due dates here. The marginal analysis, y'all, that was actually due last night at midnight. But I still looks like y'all need a little bit more time to work on that and finish that. So I went ahead and extended it to tonight at midnight. But we did do examples of marginal analysis last time. So we did examples of that. So that's in the notes from last time. So if you look back at the lecture and look at the notes, then there are examples of how to do those problems from marginal analysis. But if you need some help, you can visit John after class, and he'll show you how to do those. So it's really not that difficult. Or you can come and visit me if you want to in my office, and I'll show you how to work on that also. But again, you can look at the notes from last Wednesday. We went through some more examples of marginal analysis in the notes from last time. And also last time we started this talking about section 3.4, but we just got through one problem. So we're going to look at a lot more examples from 3.4 today, which is applying another differentiation rule called the chain rule. At first, the chain rule seems a little bit clumsy, especially the way the book wants you to fill in the homework for this homework 3.4. They make it a little bit more complicated than it needs to be. But anyway, we'll work examples like the book asks for, but then I'll show you that really what we're doing is a little bit simpler than it appears when we're trying to apply this so-called chain rule to find the derivative of a function quickly. So again, the chain rule is just a shortcut rule to help us differentiate more easily. And then we're going to look at another rule, our last one in section 3.5. This is called the product rule, which is just, again, another formula that we can use to help us find the derivative of a function in a little bit easier fashion. And then that's probably all we'll have time to talk about today. Okay, so let's see how far we get into those notes. All right. So again, if you're looking for examples for marginal analysis, look at the notes or the video lecture from last time. I think the sound, there are some sound issues with the video, so I hope that doesn't recur again today. I don't know what happened with the video lecture, but it's just short patches where you'll hear some buzzing. But those don't last very long, just a few seconds, and then my voice comes back on. So you can get through those if you're looking at the video lecture for some of those examples. And the notes are posted too. Okay. I got to figure out what's going on with our screen. It's gotten off kilter there. I don't think I can adjust that. Maybe I can. I'll have to. Well, I'll try that after class. We can see all right though for now. Okay. So let's look back and look at some examples of this so-called chain rule. So the idea of the chain rule is you've got a function. It's got to be a fairly complicated formula So the chain rule is to help us find derivatives of formulas that are a little bit more complicated than the ones that we've done up until now, okay? And the idea is you have to take that function that you want to find the derivative of, and you have to write it as a composition, okay? That's the idea behind the chain rule. And so in the homework, they're actually going to force you to do that. They're going to give you a function, ask you to write it as a composition, and then apply this so-called chain rule to find the derivative of the function. Okay, but after you've done a couple of examples of the chain rule, you'll see that it's actually a little bit easier than it appears in this long definition of the chain rule. Okay, the idea behind it is not really all that complicated. Okay, so I think after you've done 3 or 4 examples, you'll get the hang of how the chain rule really works. Okay, so what the chain rule says is that if you have a function and you have it written as a derivative, okay, I'm sorry, you have it written as a composition, okay, then you can take the product of the derivatives of the 2 functions that are involved in the composition, and that's how you get the derivative of your original function. Okay, so it's the purpose of the chain rule is to take a composition and convert it to a product. Okay, but again, just looking at this definition really is not helpful until you start seeing some examples of how that definition works in practice. Okay, so we looked at one example last time. Okay, and that was example A, so that's in the notes and the video lecture from last time. Let's start with, I've got several examples here, okay, to go through today. So let's start here with example B, okay. And a lot of these functions now are, these are a little bit kind of artificially complicated examples of functions. In practice, you probably won't encounter a function that looks like these examples. I've just made them up to sort of illustrate the chain rule. Okay, so they're probably a little artificially more difficult than they need to be in order to help you practice the chain rule. Okay, so here we have this example: a square root of 2x squared plus x. Okay, and we want to find the derivative of that function. That's our only goal there, okay? But in the instructions of, in these examples, and in the instructions in the homework too, okay, they're going to ask you first to take that function, in this case our function named f, all right, and they're going to ask you to write it as the composition of 2 simpler functions, okay, all right, before you do anything else. Okay, so let's see if we can take that function f and write it as the composition of 2 simpler functions. That's called decomposing a function. And I know you've practiced that before, but you've probably forgotten practicing that before. But you're going to be practicing a lot in these examples. Okay, so first thing I'm going to do now to start this problem is almost always what we do in calculus when we encounter a square root, okay, let's convert that to a fractional exponent first, okay, because that's going to make our life a lot easier, right? So how do we write square root as a fractional exponent? It's 1/2 power, right? Okay, so I'm going to rewrite this formula for f, okay? All I'm doing is rewriting it now, so I'm not doing anything fancy here. I'm just going to rewrite that square root as 1/2 power. Okay, so let's write that as instead of square root of 2x squared plus x, let's write that as 2x squared plus x to the 1/2 power. So that means exactly the same thing. Okay, and now what I want to write down are 2 simpler functions. They've got to be simpler functions now, because if they're not simpler than the original function, the chain rule is not going to help you at all. But I want to write down two simpler functions, g of x and h of x. That's what I'm going to call them here. We can name them something else, but I'm always going to call them just g and h, just to give them names. Okay, so that when we compose these two functions, that is when I find g of h of x, that will give me my original formula for the function f. Okay? So I want to find two functions g and h so that when I compose them, that is I take h and plug it into g, okay, as the input to g, I will get the formula for the function f. All right? That process, again, is called decomposition. That's taking a more complicated function formula and writing it as the composition of two simpler functions. Now, to do that, there's probably more than one way to write the decomposition, okay? In most of these problems, probably more than one way to write decomposition. But usually there's one way that's going to be sort of the obvious choice, okay? And that's the one that we're going to be aiming for in these examples. So you can see in this formula for f, there are kind of two things going on in this formula, right? First, you have what's inside the parentheses here, which is 2x squared plus x, right? You're taking your input x and you're squaring it and you're multiplying it by 2, and then you're adding x to it, right? So you have that expression inside the parentheses, okay? And then notice you're taking that entire expression and doing what with it? You're raising it to the 1/2 power, okay? So that gives me the clue, sort of those two separate pieces there give me the clue to what my decomposition functions are going to be, okay? So I'm going to think of g of x as just raising a quantity to the 1/2 power, okay? See that very simple function, raising a quantity to the 1/2 power. Because that's one of the things that we're doing in this formula, right? We're raising this quantity, 2x squared plus x, to the 1/2 power. So we're taking that expression and raising it to the 1/2 power. Okay? And then I'm going to think of this function h of x as what's inside the parentheses here. Okay? Which is taking x and squaring it and multiplying it by 2 and then adding it back to itself. All right? So now let's test this and see what happens when we compose these two functions. Let's see if we get the original function for f back again. All right? Well, let's see. What's h of x, again, according to what I wrote here? So I'm going to plug this in for h of x. So what's h of x? That's 2x squared plus x, right? So I'm just going to write 2x squared plus x. And then what does the function g do with its input? It takes all of its input and does what? It just raises it to the 1/2 power, right? Okay. So g of 2x squared plus x means I'm just going to take 2x squared plus x and I'm going to raise that to the 1/2 power. Okay. And that's it. All right. Is that the original function f that we started with? Those two things look the same to you? Yeah, right. They're the same. Sure. Okay. Right. So that means there that we did find the correct decomposition. Okay. There's our decomposition. G of x is just x to the 1/2 power. H of x is 2x squared plus x. Oh, by the way, now in the chain rule, this function h here that I'm feeding into the function g, that is often called the inside function. And this function g is often called the outside function. You can see how why they're called that, okay? See, that function h is inside the parentheses, right? And the function g raises its input to the 1/2 power, which is outside the parentheses here, okay? All right, now, so far, I haven't done anything exciting except write the function f as a decomposition, okay? But that's not what this problem is about, okay? It's not about decomposing this function f, okay? That's kind of an algebra problem. We're in calculus now, so what we're trying to do is find the rate of change of the function f, right? Okay? We're not just trying to write f as a composition of two simpler functions. That we have achieved, but actually what we want to find is the rate of change of the function f. And according to the chain rule now, how can you then find the rate of change of the function f? All right? Well, the chain rule says, okay, that's easy. Just take the rate of change of the function g applied to the function h, and then multiply it by the rate of change of the function h. Okay? That's what the chain rule says. Okay? So, whoops. I was supposed to write a prime here because this is the rate of change of the function h. All right? So see, the chain rule says I'm going to take the rate of change of the function g, and I'm going to take the rate of change of the function f. Hopefully those will be easy to find because these are two simpler functions, and then I'm going to multiply those two rate of change functions together. Okay? All right, so y'all can help me here. Y'all know how to find the rate of change of the function h. That's so easy. See, there's the function h. So what is its rate of change? So now y'all can, y'all have already done that on test number 2, so y'all can do that really quickly. What's h prime of x, in other words? 4x plus 1. See, I knew y'all were just spit that out in no time flat, right? That's just 4x plus 1, okay? And what's the rate of change of the function g? Okay, so that one is also pretty easy. It's a little bit tougher because you have that fractional exponent there, but it's not too bad, right? Okay, so what's the rate of change of the function g? 1/2, right? So you bring that down, and then, oops, let me try rewriting that. So you bring the 1/2 down, right? And then you have to subtract from that, so you end up with x to the what? Yeah, x to the minus 1/2, okay? So it's 1/2 times x to the minus 1/2. And then you're going to multiply those two things together to find the rate of change of the function f, okay? All right, so let's see. What does that turn out to be if I can squeeze all of that in here? So I have 1/2 times x to the minus 1/2. But be careful now, because notice in the chain rule it says you're not going to plug x into the rate of change for g. What are you going to plug in here for x? That's right, the whole formula for h, okay? You see that? So it's not just the x, but in the rate of change of g, you're going to plug in that whole formula for h. All right, so let's write that down. So we have 1/2 times 2x squared plus x to the minus 1/2, okay? And then what do I multiply in there? What's the rate of change of h? Just 4x plus 1, right, okay? So you multiply in there the 4x plus 1. Ah, there it is, okay? Well, it looks kind of like an ugly formula, all right? And I'm not going to try to simplify that formula. I could, but I'm going to get lazy here and not try to simplify it. But there it is. The rate of change of f is 1/2 times 2x squared plus x to the minus 1/2 power. Of course, you know that really means square root, right? Okay? And it's minus 1/2 power, so I can put that in the denominator. But I'm not going to try to simplify that right now. Okay? And then all of that multiplied by 4x plus 1. All right? So it's kind of an ugly formula, the rate of change of f, but at least we wrote it down. Okay? So there we have it. It didn't take too much work. Okay? All right, now let's back up and think about this, though, what we really did, okay? Because that looked like a bunch of steps there. And what I claim is we could have gotten to this answer a little bit more quickly, all right? Look at the formula for f, all right? There's our formula for f. It's 2x squared plus x to the 1/2 power, okay? Now, you know when you raise quantities to the 1/2 power, you know the power rule says to find the derivative, what do you do? You bring down the what? You bring down the exponent, right? Okay? You bring down the exponent and you subtract 1 from the exponent, okay? Notice that's exactly what we did here in finding the rate of change for f. We brought down the 1/2, right? We kept it in front of the 2x squared plus x, right? And we subtracted 1 from the exponent. So that gave us an exponent of minus 1/2. But here's the one extra part that we had to multiply in. We had to multiply in the rate of change of what was inside the parentheses. And what was inside the parentheses there? Well, it was 2x squared plus x, and you told me what's its rate of change? 4x plus 1. So what I really did here was all I really did was apply the power rule, okay? I just applied the power rule. I brought the 1/2 down, right? Subtracted 1 from it. But then I had to remember at the end, I need to multiply in the rate of change of what was inside the parentheses, which was the rate of change of 2x squared plus x. That's really all that's going on with the chain rule, okay? It's really just the power rule, okay, in disguise, okay, in this example. That's all it is. All right, let's try that again, okay, on the next example. So again, in the book's homework, they're going to want you to write this down as a decomposition, okay? And we can do that pretty easily, okay? We could do that pretty easily, but and we'll do that in just a second. But actually, I think I can skip over that decomposition part, and I think I can write down the rate of change of f here pretty quickly without having to write that decomposition, all right? Because what I'm really going to apply here is just the power rule, okay? See, here you have a quantity, right, raised to the 5th power, okay? So if I want to find the rate of change, I have a good idea of how that's going to work, right? I'm going to do what with the 5? You're going to bring it down in front, right? So I'm going to bring that down in front. So I'll have 5 times x plus e to the x to what power? To the 4th power. But here's the catch. Okay, now to finish this off, you multiply by the rate of change of what's inside the parentheses here. Okay, so if I can find the rate of change of x plus e to the x, I have to multiply that in. All right, now can we find the rate of change of x plus e to the x? I think that's pretty easy, because what's the rate of change of x? Not 0, but what? 1, right? And what's the rate of change of e to the x? That's e to the x. So I have to multiply in here. As the last step there, I have to multiply in this whole thing by 1 plus e to the x. All right? That's the chain rule. Actually, you've already been using the chain rule, okay? Just a simplified version of the chain rule. Let me show you why. Suppose I gave you this very simple formula. Let me write it down here. Suppose I gave you this very simple formula. F of x is x to the 4th power. And I said, okay, find the rate of change of x to the 4th power. You would say, oh, no problem. That rate of change is what? 4 times x cubed. But what the chain rule says is you're supposed to multiply in the rate of change of what you're raising to the power there. But what are you raising to the power? That's just x. And what's the rate of change of x? 1. So you see, of course, when you multiply in 1, it doesn't change anything. All right? Okay. So you really have been applying the power rule. You just didn't know it so far. I mean, sorry, the chain rule. You just didn't know it. That you had been applying it, okay? Because it never had any consequences up until these examples that we're doing now. Now, again, in the book, they're going to make you write down the decomposition for this function f. So let's go ahead and see if we can do that. I've already found the rate of change. This is correct, by the way. Okay, so I've already found the correct rate of change, all right? But let's go ahead and, just to make the homework happy, let's write down what our decomposition was, okay? So again, you want to write down 2 functions so that f of x is g of h of x. And the way you think about that is, okay, what's going on in this formula? Well, there's really sort of 2 things going on in this formula. First, you're raising a quantity to the 5th power. So my outside function g, I can call that just x to the 5th power because I'm raising a quantity to the 5th power. Okay? And what quantity am I raising to the 5th power? What's the inside function here? It's just x plus e to the x. Okay? And indeed, if you calculate the composition of these 2 functions, you'll see that's the right thing. Okay? G of h of x is g of x plus e to the x power, so that's x plus e to the x power raised to the 5th power. Okay? So there are the correct decomposition functions. All right, let's try this one. Oh, this one looks harder because it's got a fraction in it. Okay, but it's really not harder. Only looks harder because first we want to write this in the correct form, and that is I'm going to write it not with a fraction. So how can I change that expression so that I don't have a fraction here? Yeah, that's right. So, oh boy, y'all are learning that really good. Okay, I'm so pleased, right? Okay, I'm going to write this as a negative exponent, you see. Okay, see, that's the power of negative exponents. They help me get rid of fractions when I don't want them. So I can write this as, that's one of the powers of negative exponents. Okay, so I can write this as natural log of x plus 7 to the minus 3 power, which means the same as 1 over the natural log of x plus 7 cubed. But see, now when I've got it in this form, oh, it makes it so much easier to find the derivative, okay? Makes it so much easier to find the derivative because now I'm going to apply the chain rule and the power rule, okay? Both of those simultaneously. So let's start with the power rule. Okay, so to find the rate of change of that expression, the power rule says I would do what? Bring the minus 3 down, right? Okay, so I'm going to bring the minus 3 down, and then that will give me minus 3 times natural log of x plus 7 to what power? Negative 4, because I have to subtract 1. Don't forget you're subtracting, not adding. So minus 3 minus 1 would be minus 4. But now here's what you can't forget, okay? So you don't want to do this on the test. Now I have to multiply in by the derivative of what's inside the parentheses there, okay? I have to multiply in by the derivative of what's inside the parentheses. So can we find the derivative of natural log of x plus 7? Oh, I think that's pretty easy. What's the derivative of natural log of x? 1 over x, right, okay? And what's the derivative of 7? 0, so you just get 1 over x. So you have to remember to multiply at the end here, multiply the whole thing, so put this in parentheses, the whole thing by just 1 over x, which is the rate of change of natural log of x plus 7. Really just that easy. Is that making sense? Going to be able to do that in the homework? Yeah, the homework's going to be harder because you're not that the problems are harder, but in the homework they're going to force you to write down this decomposition. Okay, all right, which is a little bit clumsy because you really don't need to write that down in order to find the rate of change. Okay, that's kind of a formality, but the book is going to make you do that. Let's try another one. This one doesn't involve the power rule, okay, but you still have to still use the chain rule. Okay? All right, so let's see if we can find the rate of change of natural log of that whole thing, 4x squared plus 3. Okay? All right, so whenever you see natural log, you know to find the rate of change, what do you do? What's the basic idea for finding the rate of change of natural log? 1 over, right, okay? So in this case, you're going to have to take 1 over all of that, 4x squared plus 3, okay? So you take 1 over the whole thing, all right? Now, you might think, okay, I'm finished. There is the rate of change. No, you're not quite finished, okay? Because, again, you have to multiply by the rate of change of what's inside the parentheses, okay? So you take 1 over this, indeed, like you always do when you're finding rate of change of natural log, okay? But now to finish it off, you have to multiply by the rate of change of what's inside the parentheses here, okay? Which is just what? 8x. There you go. So you just multiply by 8x. Oh, that's easy to simplify. That's 8x over 4x squared plus 3. Notice that that's an interesting thing about natural log. The rate of change function doesn't have anything to do with natural log anymore. Okay, the natural log disappears from the rate of change function. Yeah, in the decomposition, the outside function here is the natural log function. And the inside function is what's inside the parentheses there, which is 4x squared plus 3. Okay? And indeed, if you were to compose those two functions, you get natural log of 4x squared plus 3. Okay? Okay, I'm going to let y'all try one, all right? So this one seems very straightforward because it involves E, okay? And you know it's so easy to find rate of change of E, right? Because you just repeat the function, right? Okay? There's one little catch here, though. This is not just e to the x. This is e to the 0.0407 times x, okay? So you do have to adjust your rate of change slightly by multiplying by something, okay? That's where the chain rule comes in. See, we found, let me show you, before you, I'll do that one. See, if I asked you just what's the rate of change of e to the x, that's so simple, you know it's what? That's as easy as it can be. It's just e to the x, correct? Okay? But the chain rule says it's not really just e to the x because you're supposed to multiply in here times the derivative of x. But what's the derivative of x? 1, okay? Of course, when you multiply by 1, that doesn't do anything, so you end up with just e to the x, all right? But in this example, notice your exponent is not quite just x, it's 0.0407 times x, okay? So think about what its rate of change is, all right? All right, so try that one. We'll see what we get. We only have one more derivative rule after this one, so I know it's getting a little bit tedious calculating derivatives, but there's only one type of rule left, so. So convince your neighbor that you've got the right answer. And if your neighbor doesn't agree, then you'll have to come to a consensus there. Ooh, I've only got a few more people I haven't called on. I've got to get through my whole list here. This person I don't know. That person is not in this class anymore. But these other people I know. Okay, did y'all write something down? All right, let's try some. Monica, is Monica here? Monica, where's Monica? Okay. Monica goes back in the pile. Albert, is Albert here? Albert. All right. Okay. So, huh? Okay, that's all right, because we'll just work through it with you. All right. Okay. So you have more than you think. All right. So to find the rate of change, Albert, right? Okay, of this ugly-looking expression, as always, we're going to take it one term at a time. All right. We're going to take it one term at a time. Right. So first, what's the rate of change of 1? That's a constant. So what's its rate of change? 0, right. Okay. So you see, you do have it. So we've got at least half of it there, because the rate of change of 1 is just 0. So that's easy. All right. Plus, and then we have to find the rate of change of that second term. Okay. But that second term should have also an easy rate of change. Right, Albert? Because that's just e to a power. So when you find the rate of change of e to a power, what do you get? You just get the same. Yeah, right. Okay. So we can write down there just the constant is not the 7.8. The coefficient there is not going to really contribute anything. So we can keep that and just repeat there e to the 0.0407x. All right. Okay, so now we're 2/3 of the way finished, right? Because e to a power, its rate of change is just, you're going to repeat e to the power, okay? But here's the one little catch, all right? If the power were just x, then you would be finished, all right? But this power is a little bit more complicated, Albert, than just x. So according to the chain rule, this is where the chain rule comes in. You have to finish this off by multiplying in the rate of change of that power, all right? So what is the rate of change of 0.0407x? That's right, yeah. So that's what we do. We have to multiply in by 0.0407, okay? And that is the final rate of change there, all right? Just multiply in times the rate of change of the exponent, okay? If that were x, if that were just e to the x power, the rate of change of x would just be 1. So when you multiply by 1, we wouldn't really notice that, right? Okay? But here we are going to notice something, because the rate of change of 0.0407x is something different than 1, right? It's 0.0407. So that does have an effect on the ultimate result, okay? Now, if you want to here, you could simplify this a little bit by multiplying the 7.8 by the 0.0407, okay? The homework may want you to do that, okay? But this is really probably far enough, okay, in most cases, all right?
What would be the g of x and the h of x?
In this example, that's a good question. So in this example, the g of x would be 1 plus 7.8 e to the x, and then the h of x would be the 0.0407x. Okay? So you would think of the h of x as being the exponent here, and then the g would be the rest of the formula. Let me show you why that's true. Let's check that, just to make sure that that's correct. So if I do g of h of x, that's g of h of x is 0.0407x. And then g, what that does is just plug all this in for x, right? So you would have 1 plus 7.8 e to the 0.0407x. Is that the original formula? Yeah, it is, right? Okay. So that's the correct decomposition. All right. All right, let's try another one just like that one. This one's almost exactly the same, okay? You have 5, a constant, plus 3 times e to a power, all right? Except here the power is just a little bit more complicated, but not much, than 0.0407x, all right? But the format is almost the same. So finding the rate of change here of this formula, very similar to finding the rate of change of this one. So try that one. Yeah, that's squared. That's x squared. Yeah, it ran into the 7 there. That's a square. So you have a double power there. E to a power to a power. Okay. So again, compare that with your neighbor. Don't get caught flat-footed here. Ooh, almost through the names. Y'all got it? All right, let's try this one. Jeremy, is Jeremy here? I think Jeremy usually sits right there, doesn't he? Jeremy, okay. He's back on. Lamb Michael. All right, I think I've called you before, but I don't know. Your number's up, so that's life. Okay. Wait. Yeah. No. Let's start out. Right. I may be wrong. Okay. Right. Okay. Don't say I'm pretty sure I'm wrong. All right. I may be wrong. Okay. But let's give it a shot. All right. Okay. So what'd you get? 3e. All right. So you got all the right elements there. Okay. I just think we need to rearrange them a little bit. All right, from what I heard you say, but maybe I heard you wrong. So you start off by just taking the derivative of 5, which is easy. That's what? 0, right. So we're just going to drop that. And now you know that when you find the rate of change of an expression involving e, you almost, 99 and 44 100% of the time, you're just going to repeat the expression, right? Okay. So that's true here also. So what did you say? Oh, yeah, that's a very strong temptation, okay, because you just want to just differentiate everything, right, okay? All right, so, but you got to resist that temptation a little bit, okay, just to start, all right? So first, you'll just repeat the 3e to the x squared, okay? So don't differentiate the x squared yet, but you are going to differentiate it, okay? Because this is the correct start, but to finish this off, we have to multiply in by the derivative of the exponent, okay? Right, that's where you're going to do the derivative. And what's the derivative of x squared? 2x, right. So we'll finish this off by multiplying in by 2x, okay? Yeah, so you had the right idea there because you multiplied in by 2 at the end, which was the derivative of 2x, right, okay? Because you had went ahead and differentiated the x squared up here, right, but you don't need to do that. First, just repeat this, Okay, just repeat this as is, and then multiply by the derivative of x squared, which is 2x. Okay, and then if you want to, you can multiply the 3 times the 2x, so you can write this as 6x e to the x squared. Okay, so almost always when you differentiate an expression involving e, you're going to get that expression back again. Okay, so you should see in your answer there e to the x squared. It's just what's the rest of it here that you're looking for. All right. The decomposition of this, by the way, I think according to the homework would be g of x would be 5 plus 3e to the x, and then the h of x, the inside function, would be the x squared. Okay. No, just x squared. Because when you compose those, let's see what we get when we compose those. You can always check your answer. When you compose those, you have g of x squared, but g of x squared, you'll just plug the x squared in for the x up here. So you get 5 plus 3e to the x squared. Yeah. Okay. And that's what we started with. Ooh, wow. That one looks terrible. Okay. And it is kind of terrible because that's a function that you would never see in practice. So I don't think, maybe I'm wrong. All right, maybe I shouldn't say that. Okay. Won't see it often in practice. Let me put it that way. All right. But there it is as an example in our homework. Okay. All right, and we want to find its rate of change. Okay. So this one doesn't have an e or a natural log in it, but it does have one of these pesky roots. All right. So you know, of course, right, that we want to rewrite that radical as an exponent. All right. So before we do anything else, let's rewrite the formula for f. So first thing, let's get rid of the cube root. So how can you rewrite that cube root as an exponent? That's to the third power, right? So you would have 1 over pi plus 2x to the 1/3 power. Now that's in a denominator, though, so I'd like to get that out of my denominator. So how can I get rid of this fraction? Right, what? Make it a negative, right. So I can write this as pi plus 2x to the minus 1/3 power. So that's the prep work you have to do beforehand, okay, before you can even think about writing down the rate of change. But once you've done that preparation, now writing down the rate of change becomes much less intimidating, okay? Especially if you don't have to simplify your expression for the rate of change when you get it. So, all right, so see if y'all can write down the rate of change now of pi plus 2x to the minus 1/3 power. And once you've got it written down, you don't have to try to simplify it algebraically, okay? Just get it written down in its raw form. That'll be good enough. Oh, this person. Okay, let's try. Aja. Is Aja here? Okay, Aja. All right. All right. So help walk me through this. All right. Yeah, you can do it. Okay. Right. You can do it. Okay. So don't fear the expression. Okay. Don't fear the problem. Right. Or it's like a horse you're trying to tame or something. Right. If you fear it, then you're doomed. Right. So. All right. So starting from here, right, Aja, okay, that looks like the power rule, right, okay? So you know how to start. What am I going to do first there? Bring down the minus 1/3, right? Okay. So bring that down, all right? And then just keep the pi plus the 2x, right? Okay. And then what do you do with the exponent there? Yeah, someone helped you there. What? Yeah, you subtract 1, right. Okay. So we'll worry about figuring out what minus 1/3 minus 1 is in just a second, all right? But now, here's where the chain rule, that's all the power rule. Here's where the chain rule comes into play, okay? Because we have to finish this off by multiplying by the appropriate amount here, right? Okay? Which is the rate of change of what's inside the parentheses, all right? So you just look inside the parentheses there, the pi plus the 2x, and you want to write down the rate of change of pi plus 2x. All right? So what's the rate of change of pi? Pi is a constant. 0, right, okay? So nothing, the pi is going to disappear. And then what's the rate of change of 2x? What did you say? 2, yeah, perfect, okay? So, see, I don't know why you were scared there, right? Because you did it right. Okay, so that's it. Okay, that's really the formula. Okay, now you can simplify this a lot. Okay, I can take the 2 times the minus 1/3, so I could write that as minus 2/3. Okay, pi plus 2x to the, and then of course minus 1/3 minus 1. I need to figure out what that is, but that's minus 4/3. Okay. Minus 1/3, subtract another one will bring you to minus 4/3, okay? And you can even keep simplifying from here because that minus 4/3, you could invert that to make that positive 4/3, and then you could write that as a radical, okay? So there's more simplification we can do here, but this is probably sufficient, all right, to stop, okay? So there we are, minus 2/3, pi plus 2x to the minus 4/3 power, that's all, okay? Yeah. All right, let's try one more, maybe two more here, okay? So now let me give you a little hint on this one because this one looks like a previous example, okay? Notice we just found the rate of change of 5 plus 3e to the x squared, right? Remember what its rate of change was? We want to remember that because this is going to be important here. The rate of change of 5 plus 3 times e to the x squared, that was 6x e to the x squared, okay? The reason I'm pointing that out is because notice that expression, 5 plus 3e to the x squared, is part of this problem also, okay? So remember, its rate of change was, what did I say, 6e to the x squared? Is that it? Did I do that right? No. 6x e to the x squared, right? Okay, so keep that in mind, all right? And let's see if you can find the rate of change here, okay? So for that function f, 5 plus 3e to the x squared squared, what would its rate of change be? Okay, so let's try that one. And since we've already done part of this problem already, maybe that makes it a little bit easier. So Letitia here, Cabrera? Ah, Letitia, okay. Right? What'd you say?
I didn't do it.
You didn't do it? Okay, well, now we're going to do it, all right? Okay, so, yeah, all right. So, okay, Letitia, when you look at that expression, you see a power, okay? So, because that square is a power, right? Okay, so that immediately brings to mind the power rule, all right? So we've been practicing the power rule today, so I know you know the power rule, all right? Okay, so what are you going to do with the exponent 2? Bring it down, exactly right, okay? So you do know how to do it, right? Okay, because that's a big piece of it. That's a big piece of it. So you bring that down, all right, okay? And then, of course, what do you do with the exponent? Yeah, you did it on test. You did it on test number 2. I think you did it well on test number 2, right? So once you bring the 2 down in the exponent, what does Letitia do with the exponent? -1, right? You just subtract 1, okay? So you're lucky in this case. You don't have -1/3 -1, which is an ugly subtraction. Here you just have 2 minus 1, okay? Right? Okay. So you get an easy subtraction there. Letitia, okay? But, so now you're thinking, oh, gee, that's good, I'm done, right? But you're not quite done, okay? Because according to the chain rule, you have to multiply in the derivative of the rate of change of what's inside the parentheses, the 5 plus 3e to the x squared. But fortunately, we already did that problem earlier. We already calculated the rate of change of 5 plus 3e to the x squared, all right? And that was 6x e to the x squared, okay? So all you have to do is, Letitia, just do what? Just what? Say it again. Yeah, and what's the operation there? Multiply, right? Okay. So just write it down and multiply there. So all you have to do is multiply in 6x e to the x squared, okay? Right? So you end up here with, let's multiply this 6x e to the x squared times this 2. So that would be 12x e to the x squared, and then what's inside parentheses here, which is 5 plus 3 e to the x squared, and all that's just raised to the first power, so I don't even have to write down that exponent anymore, okay? So there it is. Just, did I do that right? Yeah, 12x e to the x squared times that 5 plus 3 e to the x squared raised to the first power. That's it, okay? That's enough simplifying, okay? So we really don't, we could, if we wanted to, multiply and remove these parentheses, but that's really not necessary, okay? I'm happy to get to that step, okay? All right. See, so you did know what you were doing there, right? Okay? So, yeah, so you just got to be a little bit bolder and more confident. You do know what you're doing, okay? So give it a shot there. You know, you can only miss it and try again, right? Okay, on the homework, so don't be shy, okay? Great. All right, let's do one more example. So I'll do this one for you, okay? And this one also looks like a problem that we have already done, because notice that denominator we saw before, right? We saw that expression 1 plus the 7.8 e to the 0.0407x, and it was Mr. Abelero, is that, how do you say your name? Aravelo? Okay, Albert. All right. So Albert told us the rate of change of that denominator, I think, was 7.8 e to the 0.047x, all of that multiplied by 0.0407, okay? That's the rate of change of the denominator, okay? So I want to remember that. Because that's going to become important here in finding the rate of change of this formula. So, because here's how I'm going to rewrite the function f, okay? See, I don't like that fraction. That fraction is causing me heartburn. So I'm going to write this not with a fraction. So I'm going to take that entire denominator, and I'm going to write that to the minus 1 power, okay, so that I don't have a fraction here, okay, because it's kind of hard to find rates of change of fractions. You can do it, but that is troublesome. So I'd like to get rid of that fraction, so I'm going to write that as 10 times, and then that denominator raised to the minus 1 power. So these two expressions are really exactly the same, okay? I just tried to rewrite this formula so that I wouldn't have a fraction. Now, of course, the trade-off is now I have a negative exponent, but I can live with the negative exponent, okay? It's much easier to deal with the negative exponent than it is to deal with the fraction, I claim, all right, in terms of finding the derivative. Oops, I went a step too far. This is just the original, that's just the original formula rewritten, okay? That's the original function rewritten. And now let's find the rate of change, okay? When you Balkis, you want to multiply the 10 and you cannot multiply the 10 in, okay? No, yeah, because all of this is raised to the minus 1 power, okay? So I cannot multiply the 10 in. But that's okay. I don't need to multiply the 10 in because now I can find the rate of change just by using the power rule. Just use the power rule, okay? So the power rule says what? Bring the minus 1 down, right? Multiply it by the 10. Bring the minus 1 down and multiply it by the 10. And then subtract 1 from the exponent. So what's minus 1 minus 1? That's easy. That's minus 2. But now I have to finish this off by multiplying in by the rate of change of all of that. But that's what Albert already told us, the rate of change of the 1 plus the 7.8 e to the et cetera here. Okay? So we already did that in a prior problem. We know that rate of change is just this. Okay? So we multiply in at the end here 7.8 e to the 0.0407 and then times 0.0407. Okay? Whew, that looks awful. So you have this big long product here, okay? But that's it. There's the rate of change of the function f. Again, just brought the minus 1 down, subtracted 1 from the minus 1, and then I had to multiply in the rate of change of what was inside the parentheses. But I already knew what that was, fortunately, because I had figured that out in a prior example. So there's the rate of change of what's inside the parentheses, and I just multiply that in. Okay? Now you can simplify this a little bit by, multiplying it. You can't simplify it too much, but you could simplify by multiplying the minus 1 and the 10 and the 7.8 and the 0.0407. So you could multiply those constants together. But basically, that's your answer. Okay. Let's quickly look at one last example, but has nothing to do with the chain rule. Okay? Has nothing to do with the chain rule here. All right, so this is kind of like the marginal analysis homework, okay? The marginal analysis homework, but it's completely out of context. So I'm going to just give you a problem here where I want you to find the maxima and the minima of this formula, but we don't know what that formula is used for. So I don't know if that's a profit function or a cost function or a revenue function. I'm just given this formula, 2x cubed plus x squared minus 13x plus 6. And let's see what we can discover about that particular function. All right. First, this is not really a calculus problem. This is an algebra problem. It says find the x and y intercepts of the function f. Okay, the x and y intercepts. So the x-intercepts are where the graph of this function crosses the x-axis, and the y-intercept is where it crosses the y-axis. The way you would try to find the x and y-intercepts are, you always do the same thing. To find the y-intercept, you would always just plug in 0 for x, because where the graph crosses the y-axis, x is going to be 0. So you would just plug in 0 for x. In other words, you would calculate f of 0. All right? And that's real easy to calculate in this formula, because if you plug 0 in for x, what's going to happen here? All these terms will disappear, right? And you'll just get left with what? 6. So you know very easily that the y-intercept is 6. That's where this graph crosses the y-axis, is at 6 on the y-axis. Now, the x-intercepts are tougher to find, because to find the x-intercepts, that means you're going to set y, or the output, to 0. So to find the x-intercepts, you would have to solve this equation. That is not an easy equation to solve, okay? Because that is a third-degree equation. So you've got x raised to the third power. Those can be very challenging equations to solve by hand. Okay? So I'm going to cheat here. I'm going to try to find the x-intercepts just by looking at the graph. Okay? Let's just see if we can find the x-intercepts by looking at the graph. And maybe we'll get lucky and we'll have a really nice graph here. and we'll be able to see the x-intercepts. So here's the graph of that formula. I already made it beforehand. There's the 2x cubed plus x squared minus 13x plus 6. And so where does that graph cross the x-axis? Are those values easy to see? Oh, we're really lucky because they are, right? One of them is what? Yeah, right there at minus 3. And another one real easy right here at 2. And then you've got a third one, and that looks like, not 1/3, but it looks like 1/2. Let me check and see if that's right. Yeah, I clicked on it. You see that? Oh, that's exactly 1/2. Okay. So it turns out that the x-intercepts really turn out to be nice values. Minus 3, 1/2, and 2. Okay. So those we can find by looking at the graph. Instead of trying to solve this terrible equation by hand, okay? So minus 3, 1/2, and 2, those are the x-intercepts, okay? All right, so that's not calculus. That's just straightforward algebra, right? Finding a y-intercept and then finding x-intercept, that also is algebra because you're trying to solve this equation, okay? And we couldn't really solve that equation very easily by hand, so I cheated and looked at the graph, and there are the x-intercepts. Okay. The second part of the question, though, is calculus, because the second thing that's asked there is where are the local minima and the local maxima, right? Where are the local minima and the local maxima? So what we're talking about here, of course, are these points. Where is that peak turning point? And where is that valley turning point? All right? So where is exactly this point? And where is exactly this point? Okay? All right, now we can look at the graph here and get an estimate. Right? We can look at the graph here and get an estimate. But can we possibly do this without estimating from the graph? Okay? So can we do this? Can we answer this question with pencil and paper, or try to answer this question with pencil and paper? Okay? That's what I want to see if I can do here. All right? Again, where on the graph then are we looking for the local minima and the local maxima? What do we notice at those 2 points? The tangent line is what? Horizontal, right. So we're looking for this peak and valley point where the tangent line is horizontal. That's the clue, okay? I want to find where the tangent line is horizontal. And how do you determine where the tangent line is horizontal? It's where the rate of change is what? 0. Where the rate of change is 0, right? That's where the tangent line is going to be horizontal. Because remember, the rate of change is the slope of the tangent line, okay? So we've got to find where the rate of change is 0. Well, to find where the rate of change is 0, what am I going to have to find first? Well, I got to find the rate of change. So let's see if we can find the rate of change here. And can you all find the rate of change of that formula? That one doesn't require the chain rule. That one's pretty easy. What's the rate of change there? Exactly. 6x squared plus what?
2x.
Plus 2x. And then what? Minus 13, exactly. Okay? And you want to find where that is 0, so you'll just take that and set it equal to 0 and see if you can solve this equation. Okay? So we have 6x squared plus 2x minus 13 equals 0. We want to solve that equation. So Zaman says, let's try factoring it. That's a good strategy to start with. But if it doesn't factor, you can still solve the equation by doing what? Using what? The quadratic formula, right? Okay, so you know that no matter what, okay, no matter what, you're going to be able to solve this equation. You might be able to solve it by factoring, but if you can't factor, you can always solve it using the quadratic formula. So we can definitely find those x values where that rate of change is 0. Okay, we can do that by hand by using, at worst, if we have to, the quadratic formula. Okay, All right? So we don't have to just rely on the graph to find those peak and valley points. We could do this by hand, okay? All right? By using the quadratic formula to solve that equation. Okay, we're out of time then, all right? I'll fill in those details in the notes, and I'll see you on Wednesday. So start working on that 3.4 homework and finish that marginal analysis homework, okay?